Okay, this is Mr. Asher, and this is for Chem 121. And so for this video, I'm going to go through the problem set for Module 3. So let me go to that. And this is the problem set for Module 3. And it's all about composition of substances and solutions. And so for the first 3 problems, I've given you molecular structures, and I'm asking you to compute the molecular mass of the following compounds. And so I'm going to do these, one example for these, and then hopefully you'll be able to see what goes on. There's also many videos I've created that are on Canvas already for how to do this. And then, so let's look at, for example, 1B. We'll do aspirin, acetylsalicylic acid, which has the molecular formula of C9H8O4. And so if we count up all the carbons here, we'll start there. 1, 2, 3, 4, 5, 6. And then there's a 7th one there. That little vertex is a carbon. So that's 7, 8, 9. So there's 9 carbons, just like there should be. And there should be 8 hydrogen atoms. So 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 hydrogen atoms, and there should be 4 oxygen atoms. So there's 1, 2, 3, 4. So the formula checks out, and that's acetylsalicylic acid. And now how do we calculate the molecular mass of that compound? Let me go back to the whiteboard. Come on. There we go. Okay. And so the molecular mass, remember, is the mass of all of the atoms in the compound. So if we have C9H8O4, then the molecular mass, which we'll call M, is equal to the sum of all the carbon. So it's the mass of the carbon plus the mass of the hydrogen plus the mass of all the oxygen, right? And so what's the mass of carbon? Well, the mass of carbon is equal to the number of carbons, which is 9, times the atomic mass of carbon, which I'll just take as 12 for simplicity here, because carbon is about 12, right? And the mass of hydrogen is the number of hydrogens, which is 8, times the mass of hydrogen, which is 1. And then the mass of oxygen, the total mass of oxygen, is 4, because there's 4 oxygen atoms times the mass of oxygen, times the mass of an oxygen, which will take us to be 16. So 9 times 8 is 108. 8 times 1 is 8. And 4 times 16 is 64. So we add those together and we get 116. I think we get 190. Right? I think 180. Sorry, 180. 8 to 64 is 72 plus 100 is 180. So the molecular mass of aspirin, the acetylsalicylic acid, is 180. Right? It's really pretty simple. Adding up the masses, to do that, you have the number of atoms times the mass of each atom. And you can look up and get more accurate masses if you want to. I would accept if you just round them to the nearest integer. It's up to you how you want to do that, right? So that's how you do it. And it's really, really pretty simple. So you shouldn't have a problem with that. It's mainly just decomposing the formulas, right? And I've given you the molecular formulas, and you have to remember that, for example, for caffeine, which is part A, C8H10N4O2 means there are 8 carbon atoms, there are 10 hydrogen atoms, there are 4 nitrogen atoms, and there are 2 oxygen atoms. And so you multiply that all out, add them up to get the molecular mass. And the same for isoflurane, which is down in part C. Okay. Now, part 2 is percent composition. And I'll run through one of these in an example. There are several examples of this in the videos already, and I'll do one more here just for completeness, and we'll do part B, which is CS tear gas. So B is C10H5ClN2. Okay. And so I want to give the percent composition by mass of this. Whoops. Percent composition by mass of this molecule. And what that means is, first thing we want to do is we want to get the total molecular mass of this one, right? So following what we did before, we have 10 times 12, which is the mass of carbon, plus 5 times 1, which is the mass of hydrogen, sorry, plus 1 times 35.5, which is the mass of the chlorine, and then 2 times 14, which is the mass of nitrogen. So this is 120 plus 5 plus 35.5 plus 28, which is equal to 125, 35.5. I didn't do anything wrong. 28 plus is 188.5. Now, the percent mass by each of these is the total mass of that type of atom divided by the total mass of the molecular mass, right? So the percent composition by mass of nitrogen is equal to 100 times 120 divided by 188.5. The percent composition by mass of hydrogen is equal to 100 times 5 divided by 188.5. And so on and so forth. So percent composition of chlorine is equal to 35.5 divided by 188.5 times 100. And then the percent composition by nitrogen is equal to 100 times 28 over 188.5, right? And as a check on your work, if you do these correctly and you sum them together, you better get 100% or pretty close to it. You might be off by 0.1% or 2, depending on how you round. But you should, when you sum up all the different components, you better come out with 100%. If you don't, you did something wrong. So that's a good check on your work, right? So that's how you approach the questions in part 2 or question 2. And again, if that went by too fast, there's several other videos on calculating molecular composition by mass in the videos already on Canvas. Okay, so now let's look at 3, which is determine the concentrations of units of molarity, moles per liter, or mole per liter of the solute, using scientific notation, and pay attention to significant digits. So again, we'll do part B because that's the one that seems to consistently give people problems because I've got weird units in there. So let's look at part B, which is 1.03 milligrams of the enzyme carbonic anhydrase and 1.4 liters of water. As I say here, carbonic anhydrase is an enzyme used in mammalian cells that assist in respiratory function. What they do is they take carbon dioxide out of bicarbonate and they turn it into the gaseous form of carbon dioxide so that it can be expelled from your lungs. That's normally a slow process, but carbonic anhydrase is an enzyme that makes that go much, much faster. And I tell you that the molecular mass of carbonic anhydrase is 2.9 times 10 to the 4th grams per mole. So it's a big molecule because it's an enzyme, okay? So now let's go back over here to our whiteboard. Get a blank screen. And here's what we know. We have 1.03 milligrams of carbonic anhydrase, which I'll abbreviate as Ca, okay? And we have 1.4 liters of water. And we know that the molecular mass of carbonic anhydrase is 2.9 times 10 to the fourth grams per mole. And remember, this 2.9 times 10 to the fourth grams per mole, if we write that out in standard notation, is 29,000 with no decimal points because there's just two significant digits. And I tell you to pay attention to significant digits, and I want you to use scientific notation to express your answer, okay? The first thing is we recognize that this is in milligrams, and our molecular weight is in grams per mole, so we should convert milligrams into grams. And remember that there are 1,000 milligrams is equal to 1 gram, which means to convert milligrams into grams, we want to divide by 1,000, right? 1 gram per 1,000 milligrams. That's the conversion factor. So 1.03 milligrams times 1 over 1,000 grams per milligram. And milligrams cancel, leaving us as grams. So now we have, and now I'm going to switch to scientific notation, 1.03 times 10 to the minus 3 grams of carbonic anhydrase, right? Because 1 over 1,000 is 10 to the minus 3, okay? Hopefully that's clear. But there it is in scientific notation. And so now how many moles of carbonic anhydrase do we have? Well, remember, moles is equal to mass divided by molecular mass. And we can see that by the units, just in terms of units, is grams divided by grams per mole. And this inverts, which gives us grams times moles over grams. Grams cancel, leaving us with moles, right? So we want to divide this mass by this molecular mass. So moles of Ca is equal to 1.03 times 10 to the minus 3 grams divided by 2.9 times 10 to the fourth grams per mole, which is equal to a very small number. And that is equal to 3.55 times 10 to the minus 8th moles. Right? Now, is that the concentration? No, because remember, concentration is moles per liter, so we have to divide this by the volume. So the concentration, we use the chemist symbol for concentration, which is the square brackets, is going to be equal to the moles of carbonic anhydrase divided by the volume of the solution, which is 3.55 times 10 to the minus 8 moles divided by 1.4 liters is equal to 2.54 times 10 to the minus 8 molar, or moles per liter. Now, is this answer completely correct? No. Why? Because we have two significant digits here, two significant digits here, and 3 here, which means that our answer can only have 2 digits of precision. So we would write this as 2.5 times 10 to the minus 8th molar. Okay? Pretty simple. The only thing that's complicated about this is you have to convert milligrams into grams, and then the molecular mass of carbonic anhydrase is very large, so that you get a very small number, and you have to keep track of decimals, which is why we use scientific notation. Okay. The other ones are really straightforward as well. I give you molecular masses, I give you the volume. Remember to divide by the volume of water. Remember that for C, 500 milliliters, you need to convert that into liters. I'll leave that up to you how you do that. Same for part A, where you've got 342.1 milliliters. Got to convert that into liters. Okay. Number 4 on this problem set is concentration of salt in seawater. And there's a video on that. So I urge you to go look at the video I've already recorded about how to do concentrations in per mil in terms of part per thousand. And it should be relatively straightforward. Let's see, what are some of the other ones? 5 is again is an application of per mil. So let's go through that one because again, that seems to give people. So there in number 5, this is number 5. And this is concentration of HCO3 minus bicarbonate ion in seawater is approximately 2.0 times 10 to the minus 3 moles per liter. And then I ask you, what is the concentration of HCO3 minus in units of per mil? Or grams of solute, grams of HCO3 minus per kilogram of water. And I tell you here that we can assume that 1 kilogram of water has a volume of 1 liter. Okay. So that means in 1 kilogram of seawater, there is 2.0 times 10 to the minus 3 moles. Why? Because we know there's 2.03 times 10 to the minus 3 moles per liter. We know that 1 kilogram is equal to 1 liter. So that means that a kilogram of seawater has 2.0 times 10 to the minus 3 moles of bicarbonate, right? So now we have to figure out how many grams of bicarbonate this represents. And then we'll have our answer per mil, right? So we need to know what the atomic mass, the molecular mass of bicarbonate is. So we think back to HCO3. So it's 1 times 1 plus 12 times 1. There's 1 carbon. Each carbon atom weighs 12 grams. There's 1 hydrogen atom. Each hydrogen atom weighs 12 plus 16 times 3, right? So this is 48, 60, and this all equals 61 grams per mole. So bicarbonate ion with a minus sign weighs 61 grams per mole, right? So how much mass is in there? This is, remember that if we have, to get mass, multiply moles by molecular weight, which is grams per mole. We'll get grams, right? So the mass of HCO3 minus is equal to 61 times 2.0 times 10 to the minus 3, which is equal to 1.22 times 10 to the minus 1, right? Grams. So in terms of per mil, it is 0.122 part per thousand, right? Now, is this answer strictly correct? No, because we only know the concentration of two significant digits, so it really should be 0.12. Right? Okay, that's how you do 5. Hopefully that's clear. And then for 6 and 7 on this problem set, again, there are many different videos available on Canvas that I've recorded about how to do these number of moles in a particular compound, right? And in general, what you do for 6 and 7, is determine total moles of compound, and then moles of the atom is equal to number of atoms times moles of compound. So for example, if you had phosphoric acid, H3PO4, and you knew you had 2 moles of phosphoric acid, right? Then how many moles of oxygen do you have? Well, you've got 4 moles of oxygen atoms for each mole of this. So you have 2 moles total times 4 moles, 4 oxygen, 4 moles per mole is 8 moles of oxygen total. For oxygen, for hydrogen, you have 2 times 3 is equal to 6. And for phosphorus, you have 2 times 1, which is equal to 2. Right? So it's just this coefficient multiplied by the total number of moles. And there's many other examples where I've worked through that in detail to show you how that's done. Number 8, again, I think there is a video specifically for number 8 available on Canvas. Let's take a look at that and make sure. I believe if I go back to modules, you'll see that for module 3, oops, that's module 4. Yeah, worked example for module 3, assignment 3, problem 8, atoms in a wedding ring. So there's a whole entire video on that. If you're confused about how to do that, there are many different videos. There's several different videos on how to do all of these percent atomic composition ones. So I think you're set for this, and I'm going to stop here, and hopefully that gives you enough of a hint to get through module 3 problem set. All right.